Hi, I'm Robert Stein. I'm a postdoc at Caltech, and I wanted to talk to you about my recent paper, Neutrino Follow-up with the Zwicky Transient Facility, Results from the First 24 Campaigns. And just to jump right in with the topic of astrophysical neutrinos. So astrophysical neutrinos are produced through the interaction of accelerated cosmic rays with matter or photons. And astrophysical neutrinos were first discovered in 2013, but we still don't know where most of them come from. The largest neutrino telescope in the world is the IceCube Neutrino Observatory. And when IceCube detects a neutrino, they release the position of the neutrino on the sky, which is localized to a few square degrees. And astronomers around the world can then point their telescopes to that position and try and work out where that neutrino may have come from. And that's what we do with our optical telescope ZTF. So ZTF is an optical telescope located at Mount Palomar, California. And what makes ZTF special is that it has an enormous 47 square degree field of view, which means that that's more than enough to cover the localization of a neutrino alert released by IceCube. What we then do is we point the telescope towards the position of the neutrino, we observe, and then we analyze the data with our new ZTF analysis pipeline and hope to identify an electromagnetic counterpart. And although in the slide it looks very mysterious, what we're actually just doing is when we look at all of these objects that ZTF is detecting, but then we reject stars and asteroids and planets, and we require that the object has spatial and temporal coincidence with the neutrino, then we're usually only left with a handful of detected objects. And we might not know what those objects are initially, but what we seek to do is then spectroscopically observe and classify all of those objects. And at the end, what we hope to do is find an electromagnetic counterpart to that neutrino. So what might an electromagnetic counterpart look like? Well, there's actually only a few different astrophysical sources which have been predicted to emit neutrinos. So those include gamma ray bursts or supernova with choked jets, also supernova with evidence of CSN interaction or active galactic nuclei or tidal disruption events. And so when we look at our candidates and we find that a particular candidate doesn't fit one of these categories, then we are able to exclude it as an electromagnetic counterpart to the neutrino. So now let me give you the results. And what we're currently averaging is one neutrino follow-up campaign every 5 weeks. We began in 2019. And so what that means is that we're now at, as the paper suggests, 24 neutrino follow-up campaigns. The most exciting thing to come out of the program was the identification of not one, but two different likely neutrino sources. So that was a tidal disruption event that was coincident with a high energy neutrino published in Nature Astronomy last year. And then just last week in PRL, we had a second tidal disruption event coincident with the second high energy neutrino. And beyond these two exciting results, what my paper in this time was seeking to do is ask the question, what can we learn from the other 22 neutrinos where we didn't find an electromagnetic counterpart? And basically what we did was we simulated different neutrino source populations and said, how likely is it that we would have detected an electromagnetic counterpart if, for example, all neutrino sources had a luminosity of 10 to the 45 ergs per second. And what we found is that in that case, it is extremely likely we would have found an electromagnetic counterpart. And since we didn't, we can say that actually no more than 40% of neutrino sources can be so bright. So these are the first limits that we were able to set on the luminosity or function of astrophysical neutrinos. The other thing we did in the paper is we asked the question of how could we do better, because at the moment, the limit is only constraining certain types of astrophysical transients, only very bright ones. And so one thing we can do is just more. So we imagine what would happen if we took not 24 neutrino follow-up campaigns, but we imagine 48 or 96. And what we saw is that basically the limits would get increasingly strict and also increasingly constrain fainter transients, for example, supernova type 2n. The other thing we imagined is what would happen if we had a telescope that went deeper. So something like the Rubin Observatory, for example, that could observe neutrinos to a depth of 24th Mach. And in that case, we found that if we took exactly the same number of neutrinos, but we had this these deeper observations, then we would be able to much better constrain the fainter transient populations. And so this is very exciting for upcoming future research in this area, guiding us on what we might need to do better. So that was just a teaser. If you want to know more, I point you to the paper itself, which is on arXiv and has also been submitted to MNRAS. So thanks for watching.